Hi, in this module, we are going to talk about the definition of countable and uncountable sets. I want to begin by first telling you that some of the proofs that we're going to do in this module are proof by contradiction, and proof by contradiction are inherently challenging to human brain because they ask you to assume something the brain knows to be false, and there will be quite a bit of resistance to it, but please bear with me. And if there are questions, and I'm sure there will be, make sure you discuss it with us. Okay, so before I proceed, I want you to look at a couple of links on YouTube that will provide you more information on this topic. We are going to begin with review of cardinality of sets. Cardinality of set is intuitively what is the number of elements in the set. So for example, here we have the set A, and the cardinality of this set is 5 because there are 5 different elements in this set. While counting the number of elements works for finite sets, it runs into a problem when we have infinite sets. And we have seen that there are some sets that are infinite. This includes the whole numbers, integers, positive integers, real numbers. We can look at subsets of natural numbers. We could look at subsets that are finite. We could look at all subsets, including the subsets that are infinite. All these sets are infinite, so simply saying that count all the elements doesn't work because there are infinitely many elements. To deal with infinite sets, we are going to define the notion of correspondence or bijection. So let's observe one thing, that if I have two finite sets that have equal number of elements, then we can create a bijection between them. So for example, if I had a set containing, say, A, B, and C, and another set that is say, 1, 2, 3, they have the same number of elements, and in that case we can create a function something like this, which is a bijection. That means it's 1 to 1 and it is onto. We're going to use this idea to decide when two infinite sets have the same cardinality. So in other words, if there is a bijection between those two sets, we are going to say that the sets have the same cardinality. If there is no bijection, we are going to say that the sets do not have the same cardinality. So the idea that we're using is based on the work by Cantor, who defined the notion of cardinality for infinite sets by having bijection or correspondence between two sets. So we are going to say that two sets have the same size if and only if there is a bijection between them. Now we are going to be interested in one specific set, which is the set of integers, positive integers to be precise. We are going to say that a set is countable if and only if its size or cardinality is the same as the positive integers. In other words, if there is a bijection from positive integers to that set, we are going to say that the set is countable. Now the reason we are doing that is the positive integers in some sense are how we count, like 1, 2, 3, 4. So if there is a bijection from Z plus to a set, say A, then we can literally count the elements in set A by saying this is the first element, this is the second element, and so on. Note that we are going to use the word size and cardinality interchangeably. So let's look at this question. Do the set Z plus and O have the same cardinality? Z plus is the set of all integers. O is the set of all odd positive integers. Sorry, Z plus is the set of positive integers. Now we want to know whether they have the same size, and at one level we can answer it by saying how could they have the same size if one is a strict subset of the other. Now what we're going to look at is that they in fact have the same size. To see if they have the same size, we need to find a bijection from Z plus to O. So Z plus is the set of positive integers, O is the set of O is the set of odd integers. So we can create a function that says f of n is equal to 2n minus 1. So if I draw this function, it's going to be basically 1 will be mapped to 1, 2 will be mapped to 3, and so on and so forth. I can observe that this function is 1 to 1 because two numbers in here do not map to the same number here, and it's also onto because if I look at any number here, say if I look at the number 9, I can find that something is mapped to by it. In this case it will be the number 5. So because they have a bijection between them, we are going to say that they have the same cardinality. We can do the same thing for a mapping from Z plus to the set of even numbers. In this case, we will define the function f of n to be 2n minus 2. So that will map 1 to 0, 2 will be mapped to 2, 3 will be mapped to 4, and so on and so forth. So let's look at this question of do Z plus and Z have the same size? Z plus is the set of positive integers, Z is the set of all integers. To do that, let's try to line up the Z plus and Z in this way. So Z plus is as is. Z is organized as we start with 0, then 1, then minus 1, then 2, then minus 2, and so on and so forth. And what we're going to do is we're going to create a mapping where 1 maps to 0, 2 maps to 1, 3 maps to minus 1, 4 maps to 2, 5 maps to minus 2, and so on and so forth. So if we ignore this first part, which is special case, all the even numbers are mapping to positive numbers and odd numbers are mapping to negative numbers. So the actual function will need a little bit of work, but it will look something like this. For n is equal to 1, which is a special case, we map it to 0. If it's even, we map it to half of that number. If it's odd, we map it to the corresponding negative number. Here is one lemma that we can have. If I have the function from a to b, that is bijection. I have a function a to c, that is a bijection. Then we can create a function h, that is from b to c, that is also a bijection. Now, what this means is if I have shown bijection from say z plus to e and z plus to o, that means I can create a bijection from e to o. If I've created a bijection from z plus to e and z plus to z, then that means I can create a bijection from z to e and so on. And that means that all these sets have the same cardinality. Once again, we have reached to check before you go ahead slide. Here I want to emphasize that we looked at some sets like the odd numbers, even numbers that looked to be smaller than z plus, but they had the same cardinality as z plus. And that was because there was one bijection from z plus to that set. If one such bijection exists, then the two sets have the same cardinality. Note that you could have other functions from say z plus to o that are not one-to-one or not onto. That doesn't matter. If there is one function that is there from z plus to o that is one-to-one and onto, that means that they have the same cardinality. What I wanted to do at this stage is we defined a bunch of functions earlier, say z plus to o, z plus to e, etc. Make sure that you understand what those functions are and the fact that they are one-to-one and non-to.